All right, if you're interviewing for an embedded Linux job, there's one question that can pretty much make or break your chances. Today, we're going to walk through the perfect answer to absolutely nail it. This is it. This is the one. It seems so simple, right? How do you handle hardware signals in Linux? But your answer to this reveals just how deep your understanding really goes. A great answer proves you don't just know things, you get how the whole system actually works. So let's dive in. So, before we even touch on Linux, let's zoom out. Every single computer has to solve this one fundamental problem. How does the brain, the CPU, get information from the outside world? From a keyboard, a sensor, a network card, anything. And there are really two main ways to solve this: polling and interrupts. The easiest way to think about it is this. Polling is kind of like the "are we there yet" method. You're just constantly asking for an update. Interrupts, on the other hand, they're the notification method, where you just get told when an update is actually ready. Let's look a little closer at polling. The CPU literally gets stuck in a loop, over and over again, asking the device, "Hey, got anything for me? How about now? Now? Anything yet?" It is just constantly busy, doing nothing but checking. Now, here's the trade-off. The one, and I mean the one, good thing about polling is that it's super simple to write. But oh man, the downsides are huge. It is wildly inefficient. The CPU wastes something like 99.9% of its time just checking, and that prevents it from doing any other useful work. It's kind of like hiring someone just to sit there and hit the refresh button on a web page all day long. And that brings us to the much, much smarter way to do things: the interrupt. See, here, the CPU doesn't ask, it just waits. The device itself sends a hardware signal. It's like a little tap on the shoulder that tells the CPU, "Hey, I've got data for you right now." This frees up the CPU to do literally anything else in the meantime. So here's how that actually plays out. First, the device sends what's called an interrupt request, or an IRQ, along a special hardware line. And in modern systems, the CPU knows which device is on which line, thanks to a map called the device tree. As soon as that IRQ hits, the CPU immediately pauses whatever it's doing, saving its place. Then it jumps to a special predefined function called an interrupt service routine, or ISR. This little piece of code does its job super fast, and once it's done, the CPU just resumes its original task exactly where it left off. No time wasted at all. For any modern, efficient system, interrupts are absolutely the way to go. They let the CPU be this amazing multitasker instead of a single-minded pest. And this right here, this is the foundation of a fantastic interview answer. But, and this is a big but, here's where it gets a little tricky. That simple interrupt model we just talked about, it works great on a tiny little microcontroller, but in a massive, complex, multitasking operating system like Linux, that same simple approach, well, it can be incredibly dangerous. And this is the core problem. When an interrupt goes off, Linux stops everything else to handle it. So if your interrupt handler is slow, if it takes too long to run, the entire system just grinds to a halt. Your mouse freezes up, your apps become unresponsive. It's a total system killer. So how did the brilliant folks who write the Linux kernel solve this? I mean, they couldn't just get rid of interrupts, right? They're way too efficient. Instead, they came up with this really clever, really elegant architecture to get the best of both worlds. They did it by splitting all the work into two distinct halves. This driving analogy is probably the perfect way to understand it. The top half is like getting a text message while you're driving on the highway. You can't have a whole conversation, right? You just take a super quick glance to see who it's from, that's it. The bottom half, that's what happens after you've pulled the car over. Now you're safe and you can call the person back and have that full, detailed conversation. And this table really formalizes that idea. The top halves, that's the actual ISR. Its one and only goal is to be incredibly, incredibly fast. It runs in this special, restricted interrupt context, where it's not allowed to do anything slow, like sleep or block. It just grabs the data and gets out. The bottom half is where all the heavy lifting and the slow processing happens later, in a much safer environment. Okay, so how do you actually implement that bottom half? Well, the key term your interviewer really wants to hear is work queues. This is the modern, flexible standard. What happens is the top half basically just adds a task to a to-do list. Then a special kernel thread comes along later to actually run that task, safely away from that critical interrupt path.
Now, pro tip, while work queues are what you should talk about, it's also good to know there are older ways to do this, like tasklets and soft attracts. Mentioning those just shows an extra layer of knowledge. Okay, we've laid all the groundwork. We get polling versus interrupts, and we totally get Linux's top and bottom half architecture. Now, let's put it all together into that perfect interview answer.
Here it is, 4 simple parts to a killer answer. Part 1, state your method. I'd use interrupts for efficiency, and I'd configure them in the device tree. 2, introduce the Linux architecture. In Linux, you can't do very much work in the ISR, since that's the top half, which absolutely has to be fast. 3, explain the handoff. The top half just grabs the critical data and then schedules the bottom half to do all the heavy lifting. And 4, and this is crucial, name the tool. I would implement the bottom half using a work queue to safely process the data without blocking the entire system.
You see, an answer like that, it doesn't just list facts, it proves you understand the entire chain of logic. It shows you know why interrupts are better, how they're configured, the specific architecture Linux uses, the critical constraints of that architecture, and finally, the modern implementation. You've just shown a complete practical understanding of the whole thing.
With that answer in your back pocket, you are absolutely ready to impress. You've got the knowledge and you've got the structure to deliver it with total confidence.
And I want to leave you with one final thought to chew on. We've pretty much established that interrupts are almost always the better choice. But almost isn't always. Can you think of a situation, maybe a specific type of hardware, where the raw simplicity of polling might actually be the right engineering choice? It's definitely something to think about. Thanks for watching.